Great. Okay. So hi, everyone. I'm Ober Demer. I'm Director of Operations at Spectra Power. This is Jeffrey Bell, who's basically head of cell development at Lyten, which is a lithium sulfur battery company. And the two of us were two of the three authors on the industry cell chemistry development section of the battery report this year. We're really proud to share this with everyone. It was an enormous amount of work and a ton of people contributed to this. So just really quickly, I want to read off a couple names of people that contributed to different sections in this. And I'll try to also call back and highlight them when we get to kind of their pages and contributions. But just in case I missed them later, basically, aside from Jeff and I, there's another gentleman, Muda Abrushkela, who is the other author who did the most work after Jeff and I for this section. I just really want to call out his work, and I'll show the pages that he contributed the most to later. There was also Ziwen Huang, who was a contributor who worked on the NMC sections. Again, Benjamin Leisel, who contributed for the LMO. Siba Bohm, who worked on the silicon. Marco Sinischaki, who helped with the solid state section, and then Cesar Quinn, who helped with the sodium ion. And if I've forgotten anybody, I apologize. And there's a section later that will give attribution. Okay, so let's get started. So we're going to jump. Oops, that changed the wrong page. There we go. So we're going to jump right in. And basically, battery cell chemistry development is a big deal just because it's where the industry is going. And so this is the first slide of the section. It basically just kind of harks back to, early energy density and early cell chemistries. And there's a lot of information on this page, but basically, as you move from the left to the right, what you're seeing is basically over time, chemistries change and evolve, and energy density has been going up. And basically everybody on some level, all of the major companies, players, and governments are basically aiming for sort of the 400 to 500 watt hours per kg lithium metal, typically solid state batteries. That's sort of the trajectory of the industry, at least in terms of the highest performance. I'm not saying that's going to go into, EVs or grid storage. It's not, but that's where they're going in terms of the highest performance, most valuable, useful batteries for enabling new applications. A lot of links here to some specific battery programs that people are funding in the US and Europe and in Japan. And I got most of this wonderful slide, which I edited a little bit from the link there in the bottom right. So first up, some of you have probably seen this before. This is part one in a three parts of the slides here. Which is something Jeff and I put together for the Battery Brunch community a couple of years ago, but we really refined and drilled down on a lot of details for this report. And what I'm going to do right now is I'm going to change screens. And for basically the next three slides, I'm just going to show you the original, which you'll see why in a moment. So Jeff just confirmed that you can see what I just switched to.
Yeah, I can. And guys, the way to look at this is this is our best attempt to help label up manufacturing process with costs and performance. The actual costs for each of the sections, as you'll see on the right, are very specific to certain areas. That's because it's pulled from Samsung's actual costs in an industry report from USB. And we don't have it for things like solid state, right? And those are going to be different, but you have lamination and other things that we can't cost. But the idea is we're just trying to figure out and kind of give a rough idea of this is what the steps are involved in making those additional chemistries, right? And you'll see it here for high silicon, you'll see it here for solid state, you'll see it for lithium sulfur, lithium metal. And I do know there's a little bit of confusion about which one is sulfidic versus oxidic. Oxidic is QuantumScape, sulfidic is solid power. Essentially, they're just two different types of structures, and they have their own advantages and their own processing hurdles unique to each of them.
And the way to basically read this is really on a high level. It's the different macro types of cell chemistries, mostly cathode dependent for the lithium ion stuff. And then for lithium metal, it's really the cell architecture. Is it solid state? Is it just high nickel lithium metal? Is it, majority silicon, right? Those are, and a couple other things in between. But basically what this is meant to do is highlight the differences as you go through the different chemistries on the top, and then through all of them, different manufacturing processes, different cell performance for the different chemistries. And these are all basically, there's a bunch of caveats on the bottom on how we did this, but it's the goal of this is to basically give you as apples to apples comparison as possible with kind of cell designs designed for energy density, not for some of the other metrics. So you can kind of compare the performance across all of them. There are, of course, ways to design cells with all of these chemistries to change all of these attributes as you give in one section to get in another. So we tried to kind of hold our assumptions the same for many of them. And for a lot of the new chemistries where there's not good manufacturing data, there'll either be things missing or kind of qualified numbers on how we got them.
Yeah.
But as you go through this, what you end up getting is a lot of the key metrics that people care about, a color that kind of gives you a basic guideline of, is it average, better than average, or worse than average? And then matching to a lot of the preferred performance metrics of the different industries in terms of, for all of them, kind of their first, second, and third most important metric for those industries. And again, matching, is it an average, above average, or below average technology with the assumptions of a high energy performance cell for that technology for those applications.
Yeah, and I kind of want to circle back, and I know a lot of people are going to sit there and look at safety and talk about, oh, their company does the safety. There's really like 3 layers to the safety argument that we had to deal with here. There's one that is inherent to the materials used in the system. So like NMC versus solid versus lithium versus sulfur, are those materials inherently safer on their own without any safeguards? There's always going to be things you can do in the cell design to add separators or packaging that improve safety. And then there's always going to be a third layer, which is what do you do in the BMS to make it, or the battery pack in the BMS to make this chemistry or the pack safer. And we're looking at this more from the materials inputs themselves, not I'm going out to Soteria and buying current collectors that shrink away from shorts.
Or you know, triple redundant, super safe, heavier, more expensive packs, which is another option for some of the less safe chemistries. And just to show a little bit here, we also match a lot of the markets to kind of their total dollar amounts. Everything tracks through the whole way through. So it's really supposed to be one holistic document. And we broke it up in the battery report into 3 slides for the sections, just because you can't fit them all on one page and read. Again, all the people that I accredited earlier helped in some way with the data that went onto this, even if just doing their own sections in the battery report had kind of recent best effort data and publications and sources for a lot of the things we put in here. So thank you very much. Giant caveat here on how we did it and why and what our methods were. And if you disagree with something, there's a link to a document that lets you tell us what you think is wrong and why, and we will try to change it going forward so that this can be a resource for the community that's kind of updated each year. There's a section with a bunch of links on how we got the preferences and chemistries. There's some comparison data tables and graphics for people to look at here, including costs. There's its own section here on LMO that was from Ben, so thank you again, Ben. And there's also a pivot table with a bunch of current industry produced cells for a lot of the different chemistries that you can look at as kind of a comparison. So anyway, so this is basically a resource that we put together for the community. We hope it's useful. There's definitely things that can be improved on it, and hopefully with people's feedback, we can make it even better for next year.
Yeah.
So,
and one thing is to the comments, why is lithium metal marked bad for some applications, guys? I want to drive this home. A lot of the time, the application is kilowatt hours per cycle per dollar. And some materials are just inherently cheaper. They inherently cycle longer, or they inherently have more energy density. And it's kind of the combination of those 3 that's really going to dictate it for the application. A great example is government will pay you an arm and a leg for anything that helps enable their mission. Auto manufacturers will break your knees unless it's really common. Yeah, if you don't get the cost down. So there's this like butter zone, like you, the consumer, pay $1,000 for an iPhone. So we can mark up batteries a little bit more. That is okay, right? So it's really going to be dependent on what are the inputs. What is the application? We did our best to kind of line it up. Like, I don't think any of us here are going to want lithium metal next to our face. There is a safety component to that. So, Yeah.
Okay. So jumping back in slides real quick. So as you can see, these 3 slides are just pulled from those sections and they just go in order. Again, the document's available from links in all of them. It's a publicly available document. I encourage you to go look at the document, not the slides. One thing I've got in here between them is the other kind of biggest thing that I think made a really big difference in different cell chemistry performances and batteries in general in the last year and a half is the rising metal costs. And so what I did here, and I stole the graphic on the left from the source on the bottom left, and I used a bunch of information that I got that I credited on the bottom right. But basically this looks at LFP versus NMC material prices Q1 2020 to Q1 2022 And look at these increases. I mean, just astronomical, several 100% increases for the metals. Typically the cathode material, which are highlighted, and any of the lithium or lithium components. Electrolyte salts, lithium carbonate, lithium hydroxide, and just the core metals, the nickel and the cobalt and everything else, all went up astronomically. And so you look over here over time, there were some previous spikes in metals. Everyone was saying that packs were going to be going down and keep going down. People were aiming at like kind of the $100 per kilowatt hour. And you see kind of where it hit. And it's going to go back up next year. There's not enough supply. There's too much demand. And all the metals are really expensive. And high level materials are 50+% of a battery in terms of total cost. And right now, maybe they're closer to 80%.
So what does this really mean is basically, guys, it's going to be a good industry to be in, but people are going to have to diversify on their chemistries, right? I think the world has basically looked at lithium ion as kind of the AA battery, and they think they can shove it into every application. And the reality is they're going to have to change applications. And I also think as we get into the players and key sections, we're going to see difficulties, right? Because if you pair something expensive with something expensive, right, it becomes more of a luxury item, right? And the goal is to get EVs and other objects into what I would say middle income, low middle income, and even so are some of the lower income families. And there's going to have to be some sacrifices or changes in viewpoints on what is used. And that's kind of what we're doing here with this battery chemistries and applications landscape overview. So what we've kind of done is just taken 6 applications. We fully realize there is 100 more. And there's even subset applications to a lot of these applications. For example, like the one that is grid, there is grid for the utilities. There is grid for your house. There is using your car as a grid add-in to the house, right? There is the home brewers of the grid and what they put together. There's this whole levels of this, and there's grid for military installations, right? That they have travel around. So this is more of a very big overview and kind of giving you the ideas. What we've done here, left to right, is we've kind of put a table, and Ober and I are going to have to fix that left column that's awkwardly formatted. But basically what we've done is we've rated what the 3 highest priorities are by application, and then some of those sub applications in there, right? So for example, if you look at it for like planes, really with the FFA rulings, cycle life, with having to change out the battery every year, right? You're going to start focusing more on watt hours per kg. You're going to focus on rate and safety, and we're sort of reliability. Cycle life, since you're replacing the battery every year, doesn't really come into play. But when you're talking about stuff that goes into space and you won't see it for 15 to 30 years, reliability, cycle life, all of those become even more critical than, say, energy density or even watt hours per liter, right? Cost is another example that doesn't even make it or blip on there. Going to our right, if you're looking at infantry, a great example of this is suddenly safety is number 1, right? You put a pack on a soldier, it doesn't get a BMS, it doesn't get a pack structure with a built-in cooling system, and bullets are suddenly flying at it. And now you need to make sure that if a bullet somehow hits that pack or that battery, that it doesn't take the soldier out with it, right? That is the reality we need to avoid. Another great parallel to this is pacemakers that's being implanted into your body. I don't think all of us would like that to be a non-safe first approach to the battery chemistry, considering it's sitting right next to your heart. That'd be a bad day. But like computers and tablets, that's cost and watt hours per liter, right? They're going into phones, manufacturers are beating you up, and then we go there. So what we've done, if you go to the next slide, is we've kind of listed out the major players that you'll find in that spreadsheet. And what we've done is made a bunch of spider charts. I'm going to be sorry and say sorry right now. Some of these are hard to look at. There's just a lot. Some of them are easier to look at because a lot of things line up in the chemistry. So you can kind of see where things are going in terms of where their best is. Like, for example, sodium ion and load balancing is a great example. You got tons of flat land space. You don't really care about energy density or watt hours per liter. You care about cycle life and cost. And it's not only the cost of making the battery, guys, it's the cost of the poor soul who has to go out there and change the battery every time it dies with brand new batteries, right? So that gets factored in.
That's something that people don't realize a lot of times. And so if you look at, for a very simple example, but look at the little like solar power call stations you'll see on the freeway, a lot of those are deconnected from a power grid and they will have a battery. And it doesn't matter what that battery costs. If you have to send somebody it takes hundreds of dollars to ship out there and replace the battery every few years, you can afford whatever the cost of the battery is to not do that.
Bless you.
Okay.
going on. So we've kind of continued on, and then we get into this section of SWOT analysis. So I'm not going to go through each of them individually.
Yeah, and real quickly, these are credited to Muda. So there were some things like this in the last year's battery report. Muda did it for all of the chemistries that you see in here. So the NMC versus LFP, and then the LCO, and I believe also NCMA. And so he did all of these SWOT analyses, and so big credit to him for that. And his work here was also very helpful for us to do our large document. He gave us a lot of input for that. So here you'll see kind of, again, LFP versus NMC, kind of the different SWOT analysis of it. Some stuff has been moved per 2022, like cost. People traditionally said that LFP was cheaper. Well, right now it's not. and so there's some stuff like that that's been changing as people have swapped to LFP in the last year. But so here's the one for that. And the other thing Muda did is he did these wonderful production levels for the materials by player and quantity, which are really good. It's really good to understand who's doing what, who's making what the different sort of partnerships and stuff are. There's some great slides that match basically the EV companies to the cell makers to the material makers and other parts of the battery report, but here you can just see the production levels of some of the different materials. So again, here's for LFP, and then you jump through to kind of the big highlight events for LFP in the last year.
Which I want to caveat, guys, there is not enough LFP to meet supply. So every time someone announces that they are working on LFP or they are adopting LFP, the price of LFP actually goes up. You could almost match this timeline of when people announce LFP to the cost of LFP, and it's like very parallel with each other.
Mm-hmm. And there's been an enormous amount of announcements since 2021 of people switching to LFP, starting to use LFP, or announcing that they're going to be working in LFP. A lot of interest in the industry for a lot of the performance benefits and matching, but the problem is the costs have just been going up because of the low supply and high demand. This is also just because LFP has kind of been a big focus the last year or two, but sort of related similar chemistry. So LMFP and LM3P are also being worked on. There's a lot of companies that have announced sort of it's the equivalent in the NMC field of all the different versions of NMC and NCA and NCMA. It's just the same things now happening with LFP. So everyone will recognize the NMC, and again, same thing, kind of by player, by number. And then we look at kind of the previous chemistry that's now kind of phasing out a little bit more, which is LCO versus LFP, which is a little bit, again, kind of the highlight focus of this last year or two. And this is also from Muda. And then again, the makers of LCO, and you'll notice those numbers are a lot lower than the other ones, which is just because people are doing a lot more with LFP and NCA.
Yeah, I mean, you have the CO part is in the NCA and MC part, right? So they're essentially getting cannibalized by the other chemistries taking over, right? If you're looking at it from that standpoint, and you're looking at where your margins are as a materials company, and you're like, I could sell the cobalt to unit A, or I could get a better margin at unit B, you're always going to go to like person B and sell for that better margin. And
the high level comparison there is LCO is kind of 180 to 200 watt hours per kg energy density versus a lot of the high nickel content like NMCs are more like 260, 280, but it costs more for LCO because the cobalt is so expensive. And so naturally, you're going to use something else if that's what you want. It's one, higher energy density, and two, it's lower cost. All right, so this is all you.
All right, guys, I work on lithium sulfur, so I'll take on this one. This is just the SWOT analysis for lithium sulfur, right? Kind of some obvious things is strengths are going to be costs, weaknesses, right, are going to be in power. But we go through and you can kind of see it. And once again, this was actually thanks to my buddy, Zach, who I work with at Lighten, and he helped put this slide together. So continuing on, we kind of go to the Bear Q.
Hi.
Oh, sorry.
Going on, we go to kind of the notable events. Relative to the other slides, there aren't as many here. Sulfur is kind of a small field. It's really advanced technology. But the key things here you're really seeing is a lot of companies either emerging, or you're seeing a lot of government push into these companies for specific applications. And that's NASA, right? Or DOE, or even some more of the aerospace based companies.
And oh, look at this, a sponsored slide from Lighten. How did that get in the battery report? And the answer is Lighten's one of the sponsors of the battery report. And thank you very much to them for paying. One quick thing I would like to say is we put a lot of effort, me, Muda, Linda, and Yen, into going over, because Lighten was a sponsor, triple checking everything for the lithium sulfur stuff and making sure that it was as accurate and unbiased as possible, especially because it was provided by someone that worked at Lighten. So anyway, just wanted to throw that out there, but thank you again very much to Lighten for sponsoring the report.
Yeah, and go check them out. As I try to stay as impartial and as neutral as I humanly can on these talks, especially for a company that I work for. But do your own research as we kind of preach, check them out, do the fundamentals, and see what it's about if you want. But as usual, just check it out, do the research. All right, this is just kind of the small world. As we get down in the applications tables, what you'll see is we get to like solid state or silicon, and there's like 50 of these players. You go from there. But here's kind of what we did. This is our standard analysis for most companies, right? We're telling you the amount of employees, the amount of patents, how much money they've gotten, give you remarks to kind of give it you at the stage. Review it on your own time, but the general rule of thumb, right, is usually if a company has a lot of patents and a lot of employees, they've kind of overcome some development stages that allow for investors to want to be interested in them. Usually speaking, if a company has 5 to 10 people, there's still a lot of development work. And if there are 1 or 2 patents, it means that they're also having a hard time breaking into the space, or the finances aren't there for them to get really aggressive on the patenting side.
Okay. So now we're going to go to sodium ion. And earlier I said who was doing that, and I'm just double checking my notes real quickly, but that was Cesar Quinn. So thank you very much for him for his work on the sodium ion stuff. So these are just sort of announcements. Well, sodium ion's been around for a while. Recently, there's been a lot more interest. And so sort of 2021 to now, a lot of news events and announcements and people looking at it for applications where it fits. So there's some interesting stuff there. A lot of players looking at it, including people like CATL, who announced that they're moving towards it, probably in part because of all the cost increases for the other chemistries in the last 2 years. Because one of the plays that NAIM has is that it's cheaper. And now everyone's favorite topic to argue about, solid state. And again, thank you very much to Marco Sinischaki for his work on these solid state slides. I don't know how much people want us to go over what solid state is or how it works, but the thing I would like to just highlight is there is no one solid state. And the reason that out of all the chemistries that we did, solid state's the only really one that we did multiple of the same thing for. And we only picked 2. We picked sulfidic and oxidic. And there's a lot of other ones. And there's a lot of subsets between them. And as you can see here from the diagram on the bottom, they have very different spider diagrams on their performance. And so while most of them, if not all of them, are usually aiming towards using basically high nickel content in lithium metal, there's a lot of differences between the actual solid state materials and the systems, and whether they're semi-solid state using liquid electrolyte or actually solid state.
And the big thing here that I'd also like to mention, guys, with solid state is that it's mainly a manufacturing hurdle that is preventing mass adoption, right? There is going to be some of these polymer, sulfidic, oxidic, composite polymer, solid state electrolytes that have both sulfidic, oxidic, and polymer all mashed together, like Amir was saying, but all of those really boil down as to how do you manufacture this effectively with high yields, and that is the biggest challenge and low cost that this is currently fighting. So that's kind of not captured here, but that's actually the main hurdle right now. So you see people say solid state a lot in some applications, but usually those are going to be semi-solid is probably the more accurate term, as they tend to wet the cathode or something of that nature to help with rate or flexibility of the structure.
And that's where you lose some of the perceived safety benefits for solid state. The other thing, just to kind of point out again, is kind of a conceptual thing, but most solid state batteries are really more of a solid state material making process. And a lot of times it's, something like a PVD or a CVD or a, ball milling of nanoparticles, or, high temperature, high pressure hip pressing. And so it's a processing technique. And a lot of times there's a lot of different materials you can make with it that can go into the standard materials in lithium ion anode, the cathode separator, electrolyte. People are working on a very wide range of solid state materials using a lot of different processes and a lot of different materials. So it's one of the most interesting and actually kind of like different from company to company places if you're really interested in the chemistry. So highly recommend you look at this sort of stuff a little bit more. Tons of events in solid state in the last couple of years, and you guys have all seen these constantly. Everyone, I think everyone in the battery industry knows QuantumScape at this point. But a lot of other companies have announced solid state batteries or have announced manufacturing of solid state batteries in the last couple of years. Enormous amount of investment has been put into this industry, and a lot of time and attention and focus and hype.
Mm-hmm. And one thing you'll see here is it might be confusing that StoreDot is inside of this as they market silicon. But I just want a clarification. StoreDot is a charging algorithm more so than it is actually the materials. They tend to buy their materials from outside people. So like Group14, I think, supplies for StoreDot. So they're more about how do you charge the battery than they actually are. So that kind of applies to multiple chemistries.
And the other thing, again, is that basically there are so many different materials, processes, and equipment that can make a solid state material. And just because you have a solid state material in your battery does not make a solid state, or especially not a full solid state battery. So solid state gets misused a lot. And these announcements, a lot of times these companies have a solid state material or a set of solid state materials and or a battery with a solid state material. So just to clarify, here's sort of the, go ahead.
As I say, this is going to be different than the last one we did. It doesn't have the patents or the employees. The reason we chose a different approach really is the partners were more readily available, and you can kind of check kind of how well a company is doing by who is giving you money from industry, more so than where's the private money coming and what do they have. So right, for example, if you have like BASF invested in you, or you have a Honda or a Ford, and I know we all subconsciously attribute different levels of prowess to different companies, but you can kind of tell where people are hinging. You can see StoreDot's got a ton of money thrown at them from people we all know. And then you can kind of see a lay of the land. And the most interesting thing you can actually do with these charts, everyone, and we didn't do it here, is that you can look at companies, instead of looking at it as what companies invested in what battery startup, you flip it and you get forward and you see where they laid out all their money, and you can start tracking in which chemistries the company is actually most interested in, or what applications and fields,
and what they're basically betting on. And a lot of times it's some variation of supply chain integration and margin stacking and investment in something, and also supply investment procurement. So there's a lot of overlap here in these. But the other thing you'll notice in a lot of these is there's a lot of sort of, I guess I would call them higher end application companies that are investing in these basically enabling technology companies, right? These are not going to go in grid. These are going to go in high-end products. And so you kind of need a high-end product that demands a margin to be able to afford the more expensive, more useful battery.
Yep. Going on, we have the silicon anode. I don't think we need to spend a huge amount of time here. I think it's a little bit more straightforward than the solid state, which has a bunch of different subsets. The main takeaway from this is silicon's a very much an enabling material for the current chemistry, as it doesn't really change the manufacturing process. The bigger issue really is just the volumetric expansion. It tends to fracture upon itself as it runs into other silicon particles, which then consumes electrolyte, which then dries out your cell, which then hits cycle life and degrade the electrode at the same time. And then there's also a safety issue, which silicon burns at 2000 C. So once you ignite it, you start melting things very quickly, as most stuff is not 2000 C tolerant inside of a battery. But definitely an enabling technology. And what you're seeing today, really, people are putting 3 to 8% inside their batteries. Shin-Etsu is a great one, BTR, another one of the suppliers. They can either be a silicon oxide or pure silicon content. But definitely a cool technology. And this is just meant to give you kind of an overview of the chemistry itself. More of the players in it, we see StoreDot arrive and Group14 on the same slide, which I always find ironic. But you can kind of see it. There's a lot of silicon players in the space. But I think for this slide, the one thing I want everybody to take from this is that if you are looking at companies that are getting into the silicon game now, I would avoid those. And the reason being is there is very little. You don't have an electrolyte and a cathode to put patents around. You have primarily just the synthesis process of the material itself. And there's only so many ways you can crack silane, and there's only so many ways you can take metallurgical silicon or metal grade silicon, or like any of those and do something to it. And that space of patent technology is being rapidly filled. So if you weren't in silicon 3 to 4 years ago, you are most likely not going to be able to get a competitive edge if you're entering today.
And you look at the start dates for some of the companies that you've heard about recently who have IPO'd or SPAC'd or et cetera in the last couple of years, Innovate 2005, Enovix 2007, Amprius, which just SPAC'd last September and IPO'd 2008, right? They've been going for a very long time, a lot of investment, a lot of time, a lot of patents. And silicon's one of the interesting things because it's both a new technology and it's an additive to all current lithium ion, because again, you add it to basically the graphite for any of the other cell chemistries in a tiny percent to get a little bit more energy density, a little bit faster charge rate, which are very valuable. But there's a lot of different ways you can do it. And a lot of these companies, some of them are cell makers, some of them are material makers, some of them are both. And it's a very filled space because it's basically an additive enabling technology on top of everything else. And it's something that you can kind of get the materials for and manufacture anywhere, which is very appealing right now. So if you look at the IRA funding for the first couple rounds of stuff, they've put a lot of money into silicon. So they put stuff into Amprius, they put stuff into Scylla, they put stuff into Applied Materials for their pre-lithiation of silicon batteries and other companies. So interesting space, a lot of new technology. And I think that concludes our presentation for today.